The electrical code, specifically the National Electrical Code or NEC, is a comprehensive set of standards designed to ensure the safe installation of electrical wiring and equipment. However, certain aspects of the code are frequently misunderstood, leading to potential hazards and code violations. This explanation aims to clarify some of these common misconceptions. Firstly, let's address the concept of grounding versus bonding. Grounding refers to connecting electrical circuits and equipment to the earth. This provides a path for fault current to flow back to the source, allowing overcurrent protection devices like circuit breakers or fuses to operate and clear the fault. Bonding, on the other hand, involves connecting metallic parts of the electrical system together to create a low impedance path for fault current. This includes things like metal conduits, enclosures, and equipment grounding conductors. The purpose of bonding is to minimize voltage differences between these metallic parts, reducing the risk of electric shock. A common misconception is that grounding and bonding are the same thing. While they are related and both essential for safety, they serve different functions. Grounding provides a path to earth, while bonding ensures equipotentiality. Secondly, consider the proper sizing of conductors. The NEC specifies requirements for conductor ampacity, which is the maximum current a conductor can carry continuously without exceeding its temperature rating. A frequent mistake is to simply choose a conductor size based on the rating of the overcurrent protection device. However, the conductor ampacity must also be adequate for the load it will serve, and adjustments and corrections may be required based on factors like ambient temperature and the number of current-carrying conductors in a raceway. For example, NEC Table 310.15b16 provides ampacity ratings for conductors based on insulation type and temperature rating. However, if the ambient temperature exceeds 30 degrees Celsius, a correction factor must be applied to reduce the allowable ampacity. Similarly, if more than 3 current-carrying conductors are installed in a raceway, adjustment factors in NEC Table 310.15 cone must be applied. Failing to account for these factors can lead to conductors overheating and potentially causing a fire. Thirdly, let's examine the requirements for ground fault circuit interrupters or GFCIs. GFCIs are designed to protect people from electric shock by monitoring the current balance between the hot and neutral conductors. If there is an imbalance of 5 mA or more, the GFCI will trip, quickly interrupting the circuit. The NEC requires GFCI protection in various locations, including bathrooms, kitchens, garages, and outdoor areas. A common misconception is that GFCIs are only required in wet locations. While wet locations are certainly a major focus, the NEC also mandates GFCI protection in other areas where there is a higher risk of electric shock, regardless of whether water is present. For example, GFCI protection is required for receptacles serving kitchen countertops, even if they are not near a sink. It is important to carefully review the NEC requirements to determine where GFCI protection is needed. Fourthly, understand the proper use of arc fault circuit interrupters or RFCIs. RFCIs are designed to protect against fires caused by arc faults, which are dangerous electrical discharges that can occur in damaged or deteriorated wiring. The NEC requires RFCI protection for branch circuits supplying outlets or devices in dwelling units, with some exceptions. A common misconception is that RFCIs are a replacement for GFCIs. While both devices provide important safety functions, they protect against different hazards. GFCIs protect against electric shock, while RFCIs protect against fires caused by arc faults. In many cases, both GFCI and RFCI protection are required in the same location to provide comprehensive safety. Fifthly, consider the rules regarding box fill. The electrical boxes are used to enclose wiring connections and protect them from damage. The NEC specifies requirements for the maximum number of conductors, devices, and fittings that can be installed in a box based on its size. Overfilling a box can damage conductors, create a fire hazard, and make it difficult to safely work on the wiring. The box fill calculations are based on the volume of the box and the volume occupied by each conductor, device, and fitting. For example, each conductor that originates outside the box and terminates inside the box counts as one conductor. Each equipment grounding conductor entering the box counts as one conductor, regardless of the number of equipment grounding conductors. Device yokes, such as switches and receptacles, count as two conductors. Failing to properly calculate box fill can result in code violations and unsafe installations. Sixthly, review the rules for wiring methods. The NEC specifies various wiring methods that are permitted for different applications, such as rigid metal conduit, electrical metallic tubing or ENT, non-metallic sheet cable or ROMIX, and flexible metal conduit. Each wiring method has its own requirements for installation, support, and protection. A common mistake is to use the wrong wiring method for a particular application. For example, non-metallic sheath cable is generally not permitted in commercial buildings or in hazardous locations. It is crucial to select the appropriate wiring method based on the specific requirements of the installation. Seventhly, learn about the requirements for overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. The NEC specifies requirements for the proper selection and installation of overcurrent protection devices, including their ampacity rating and interrupting rating. The ampacity rating of the overcurrent protection device must be matched to the ampacity of the conductors it is protecting. The interrupting rating of the overcurrent protection device must be sufficient to safely interrupt the maximum available fault current at the point of installation. A common misconception is that any circuit breaker or fuse can be used as long as it has the same ampacity rating. However, it is also important to consider the interrupting rating to ensure that the device can safely clear a fault. Eighthly, ensure proper labeling and identification. The NEC requires that electrical equipment and circuits be properly labeled and identified to facilitate safe operation and maintenance. This includes labeling circuit breakers, switches, and panels with their intended purpose. It also includes identifying the voltage and amperage of circuits and equipment. Proper labeling helps prevent accidental contact with energized parts and makes it easier to troubleshoot electrical problems. A common mistake is to neglect labeling or to use unclear or inaccurate labels. It is important to use permanent and legible labels that clearly identify the function of each component. Ninthly, let's discuss the rules for working space around electrical equipment. The NEC specifies minimum working space clearances around electrical equipment, such as panels, switchboards, and transformers, to provide adequate access for maintenance and repair. These clearances include minimum depth, width, and height requirements. The working space must be kept clear and unobstructed. A common violation is to block the working space with storage or other equipment. It is essential to maintain the required working space clearances to ensure the safety of electrical workers. Tenthly, be mindful of the requirements for electrical inspections. Most jurisdictions require electrical work to be inspected by a qualified electrical inspector to ensure compliance with the NEC and local codes. It is important to obtain the necessary permits and schedule inspections at the appropriate stages of the project. Failing to obtain inspections can result in fines, delays, and potentially unsafe installations. It is best to consult with the local electrical inspector to understand the specific requirements in your area. 11thly, consider voltage drop. Voltage drop is the reduction in voltage that occurs along a conductor due to its impedance and the current flowing through it. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. To minimize voltage drop, it may be necessary to increase the size of the conductors or reduce the length of the circuit. Voltage drop calculation should be performed to ensure that the voltage at the load is within acceptable limits. 12thly, understand the requirements for surge protection. Surge protective devices, or SPD, are designed to protect electrical equipment from voltage surges caused by lightning, utility switching, or other events. The NEC requires surge protection in certain applications, such as dwelling units and critical facilities. SPD should be installed at the service entrance and at downstream panels to provide comprehensive surge protection. A common misconception is that surge protection is only needed in areas with frequent lightning strikes. However, voltage surges can occur anywhere and can damage sensitive electronic equipment. 13thly, review the requirements for emergency systems. Emergency systems are designed to provide power to essential equipment during a power outage, such as exit lighting, fire pumps, and life safety systems. The NEC specifies requirements for the design, installation, and testing of emergency systems. Emergency systems must be supplied by a reliable power source, such as a generator or battery system. Regular testing and maintenance are essential to ensure that the emergency system will function properly when needed. 14thly, consider the requirements for hazardous locations. Hazardous locations are areas where flammable gases, vapors, dust, or fibers are present, creating a risk of explosion or fire. The NEC classifies hazardous locations into different classes and divisions based on the type and concentration of the hazardous material. Each class and division has specific requirements for electrical equipment and wiring methods. It is crucial to carefully review the NEC requirements for hazardous locations to ensure that the electrical installation is safe and compliant. 15thly, let's discuss the rules for swimming pools and spas. Swimming pools and spas present unique electrical hazards due to the presence of water and the potential for electric shock. The NEC has specific requirements for the grounding and bonding of pool equipment, the location of receptacles, and the use of ground fault circuit interrupters or GFCIs. It is essential to follow these requirements carefully to ensure the safety of swimmers and bathers. 16thly, let's address the importance of continuing education. The electrical code is constantly evolving as new technologies and safety standards are developed. It is important for electricians and electrical contractors to stay up to date with the latest code changes through continuing education courses and training programs. The NEC is updated every 3 years, so it is essential to review the latest edition to ensure compliance. 17thly, there is the issue of using listed and labeled equipment. The NEC requires that electrical equipment be listed and labeled by a recognized testing laboratory, such as Underwriters Laboratories or UL. Listing and labeling indicate that the equipment has been tested and meets safety standards. Using unlisted or unlabeled equipment can create a safety hazard and may violate the code. It is important to check for the listing mark on all electrical equipment before installing it. 18thly, it's vital to understand the difference between branch circuits, feeders, and services. A branch circuit is the portion of the wiring system that extends beyond the final overcurrent protection device protecting the circuit. A feeder is the circuit conductors between the service equipment, or the source of a separately derived system, and the final branch circuit overcurrent device. The service is the conductors and equipment for delivering electric power from the serving utility to the wiring system of the premises served. Misunderstanding these definitions can lead to incorrect application of code requirements. 19thly, let's consider the neutral conductor sizing. The neutral conductor carries the unbalanced current from the phase conductors in a three-phase or single-phase system. In some cases, the neutral conductor may be permitted to be smaller than the phase conductors, but only under specific conditions outlined in the NEC. For example, in certain types of circuits with nonlinear loads, the neutral conductor may need to be oversized to handle harmonic currents. It is important to carefully review the NEC requirements to determine the appropriate size of the neutral conductor. 20thly, let's consider the grounding electrode system. The grounding electrode system provides a connection to earth for the electrical system. The NEC specifies various types of grounding electrodes that are permitted, such as ground rods, ground plates, and metal water pipes. The grounding electrode system must be properly installed and connected to the equipment grounding conductor system. A common mistake is to use an inadequate grounding electrode or to improperly connect it to the system. 21st, consider the specific rules regarding electric vehicle charging systems. With the increasing popularity of electric vehicles, it is important to understand the NEC requirements for electric vehicle charging systems or EVs. The NEC specifies requirements for the location, wiring, and protection of EVs, including the use of GFCIs and dedicated circuits. It is important to follow these requirements to ensure the safe and reliable charging of electric vehicles. 22nd, there are requirements for renewable energy systems like solar photovoltaic or PV systems. Solar PV systems are becoming increasingly common as a source of renewable energy. The NEC has specific requirements for the design, installation, and operation of solar PV systems, including the wiring methods, overcurrent protection, and grounding. It is important to follow these requirements to ensure the safe and efficient operation of solar PV systems. Finally, remember that the NEC is a complex and comprehensive document. It is essential to consult the codebook directly and to seek guidance from qualified professionals when needed. This explanation has covered some of the most common misconceptions, but it is not a substitute for a thorough understanding of the entire code. By understanding and applying the NEC correctly, you can help ensure the safety of electrical installations and protect people from electrical hazards.